there was one particular problem where we have to sort of relate, and if we back up a little bit and sort of get a little bit more abstract about how we're solving these problems, one way that we're doing this is with the equations. And the equations are an analytical way of solving the problem. They are a mathematical crank that we can turn. As long as we operate the crank properly, it's going to work. But then the graphs are a geometric or a visual way of solving those problems. So things like steeper is faster, that's a kind of visual question. And you could imagine questions on the quiz that refer to that we don't need numbers, we just need to know which is faster or something like that. Great. So what we need to do in our last hurrah here for these videos is we need to put them together and do them at once. So if you were sort of paying attention to the last question, what we did here was we started with a graph and then we moved to an analytic solution or an algebraic solution. We're going to go this time in reverse. We're going to start with an analytic solution and then we're going to move to a graph. So let's suppose that we have a sort of hockey net situation and we've got a teensy tiny puck that is hit and is whipping towards that net. Instead of going from position and time and then finding velocity, let's instead go the other way. Let's go from velocity and time to distance. Let me add some numbers so that's less abstract. So a blues player hits a hockey puck and it goes 50 meters per second is probably too fast. Let's go 25 meters per second. It's moving at a wicked fast 25 meters per second, and it takes 2 seconds to get to the goal. The question then is, how far away is the goal? Also known as, what is the distance to the goal? What's the x, the delta x to the goal? Now, there's actually a whole bunch of ways to do this. And several of you in the alien problem in class today did a version of this that just ended up sort of you thought about it and you found the answer. And that's great as long as you can argue for it. So what several of you did before is in your brains, you drew time and position, and you said, well, at 0 seconds, it's at 0 meters. At 1 second, it's at 25 meters. And then at 2 seconds, it's at 50 meters. That's great. That's actually, if we wanted to be precise, and why not be precise, that actually is a third way of solving problems. And that is what we'll call numerical. And numerical ways of solving problems are great, so long as you can justify what you've done. And drawing a little table like this with time and position, that actually is a justification for how you solve this problem, even though you didn't follow the equation in the exact way, which is great. I'll take it on a quiz. So the question becomes again, how far is the goal? Method number 1 gives us 50 meters. Let's try method number 2, which is v equals delta x over delta t. Well, we know v and we know delta t and we don't know x. So in the way that some of you wrote, we could write it like this. 25 meters per second is our v. X, we don't know. And delta t equals 2 seconds. So we could sort of say to ourselves, what number divided by 2 gives us 25? You don't have to be a math nerd to see that that is 50 meters. So what do you know? that corresponds to the answer that we had found in the other way, which is great. And then finally, the sort of, I don't want to say best, but the most mathematically safe and rigorous way to do this is, instead of using this little question mark, which is basically fine, all that we do is we just change this little question mark to what we were looking for, which is delta x. And then all we do is one step of algebra. So if we started here, and I'm going to suppress the units just so that we have less letters to look at. And I'm going to suppress the delta so that we have less letters to look at. We end up with this. 25 equals x divided by 2. Now right now, we can see that that's 50 because I gave you nice numbers, because I was feeling nice. But if I didn't give you a nice number, if I gave you something like 13.6, it might be a little harder for you to just intuit the answer, especially if it was a decimal down there. But forget that for a second. Let's come back to our 25. Now here, this is the line in the sand that we called the line between middle school and high school, which is the algebra line. So we're just going to hop across that line there, and we're going to remember that we want to solve for x, which means we want to get it all by itself. And the way that we do that is we do the opposite of what's happening on this side. So our math rule was that you could do whatever you want as long as you do it to both sides and you follow the rules of mathematics. So we're going to multiply both sides by 2. And that means we get 2 times 25, which is 50. And then x divided by 2 times 2. I could rearrange that as this. Or I could just cancel them. But if we don't know how to just cancel them, we could rearrange it like this, because that's what the laws of division and multiplication allow. And then we remember that 2 divided by 2 is 1. Okay, we remember that 2 divided by 2 is 1. So if we're being fancy, 50 equals x times 1. Well, x times 1 is just x. So x equals 50. We're looking for distance. It's going to be meters. And oh, look, we find the same thing. So there's multiple ways to solve this problem. We can do a numerical solution. We can do an analytical solution in the form of our question mark treatment, which is totally fine. I'm 100% fine with you thinking this way. Question mark is equal to what? It might work sometimes. And then the sort of most precise way to work through it is to do an algebraic solution where we solve for x. And we're going to get more practice with that as the year goes on. Now, as promised, we need to double sort of check and make that all fit together. So in a position versus time graph, where our units are meters and seconds, we start at 0. It takes 2 seconds, and then we have to label this properly, which is 50 meters. Now we know that we can find the proper, precise distance given what we were given. Cool. So just wrapping up everything that we did so far. For the quiz, we're going to focus primarily on the velocity, position-velocity relationship, and this master kinematic equation, noting that we're going to ignore acceleration for now. We're going to focus on position versus time graphs because those are crucial. We're going to focus on questions like this, where we sort of have to interpret and understand what we're doing, and then we're going to look through the different kinds of scenarios, parabolas, diagonal lines, horizontal lines, comparing lines, and then, like we looked at in the last video, the sort of 4 different situations where we have rest to a bold there, where we've got rest, where we've got returning, we've got constant speed, and we've got constant acceleration. Wow, that's hard to read. But if you're confused, it's in the video that I put up before I put this video. Good luck with the quiz. Should be no tricks. See you in class.